The car is now moving nicely, staying on the right side of the road and navigating this maze quite well. But what will happen if we add some markings? Well, nothing. The car has no idea they're even there. We need to add more sensors and update the logic for them as well. The new network will have 5 inputs this time, so get ready to navigate in higher dimensions. Get it? 5 inputs means a 5 dimensional space. And no, 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 no.
Gonna code, debug, and have fun. Coding with Radu, coding with Radu. Gonna prototype and design. Coding with Radu, coding with Radu. Let's code now.
Start the playground from the link in the description, and you're gonna see this scenario, which is pretty similar to the last one, but it has also these markings on the road, like the stop marking and the traffic lights. Now, the way we're gonna solve this problem is the car is equipped with 2 new sensors. They are not really visible here, but if you're gonna turn on the manual override and go forward like this, you're gonna see that this red sensor appears here. It's overlapping the other one. The way I implemented this on top of the code from phase 1 is I just added a stop sensor, another sensor to the car, and it has only one ray here that is casted in front. But it's looking for borders from these markings instead of the road. One other thing that I did is the car is only seeing this border if it's looking at it from this angle. Like if I'm going to go up here slowly and look at the stop like that, it doesn't see it. It doesn't turn red. You could model this logic in the neural network as well, but that will make it even more complicated, and you'll see today it's going to be quite complicated by the end. Now let's go back here and see the input node associated with this sensor. So it's this one here. It works pretty much the same as the front one, but it's the distance to the stop marking there, not to the side of the road. So you can see that value changing like this, and it's 0 if it doesn't see anything. Now for the traffic lights, the same thing, but a different input node, a different sensor in the car object as well. And you can see those values changing. But if the traffic light is green, then this sensor is not reading anything. So it only looks for yellow or red traffic lights. And the same thing applies as before. If you're looking at some traffic light from the wrong angle like this, then it's not going to trigger anything. You need to look at them from the correct angle, like this, assuming that you're driving on the right side of the road. So 2 new nodes here. And stop to think about it. When we had one node, we were using that to define a line. 2, they were defining a plane. 3, we had this hyperplane. What are these? Well, they're also called hyperplanes. Anything after 3 dimension is just hyper. But visualizing or understanding what is going on now when we build this new network is going to be much more challenging than anything else, because we are not anymore in the 3D world that we are used to. So let's start solving this problem, and we're going to start from scratch. I'm not going to load any version of the car from previously, because I think recapping what the logic is helps to understand how we complement the logic. So we will build the same car that follows the right-hand rule of solving mazes as previously, but a little bit different. You'll see. Let's move this sensor for detecting the right side of the road there, and the turning left and right Let's get them out of the way for now. And here, let's focus on moving forward and stopping. We're going to focus on moving forward, actually. And for that, we need the forward sensor so that we can detect when the car is going to stop, and the speed so that we can control stopping at different moving rates. Now, let's create a new node here, like this. And two more, one like this, and one like this, and one like this. You can probably tell something crazy is going to happen. But we begin with the very basic logic here. So let's define this weight to be -1, -1, and this one was -90%, like this. And all of these weights here, I'm just going to put plus 0.1 so that this node just, whatever it is, it's going to sync with this node, and this will sync with that node, and this will sync with that node. So the logic here is really simple. What is happening here? Whatever this value is just transfers to all the other ones. And you can see here on this axis that that just means the car is going to accelerate until it's very close to the border. So like if we are going really, really close to the border, then it doesn't accelerate anymore. And this line moves here when the car is moving. Oops, I crashed it. Let's restart this. The reason why that line moves like that is because of the speed. So because this is still a 2D scenario, we can put here this one like that and see the decision border here. So now the car should be able to go forward and stop whenever. Oh, it's gonna crash because I didn't connect the reverse. So here we are going to do a not. Whenever this one is on, this will be off, and vice versa. I'm just gonna put here -0.1 and -0.1. And if this is off, 0 multiplied by something is 0, it is greater than -0.1. But if this is on, then -0.1 is not greater than -0.1. So this node, whatever it's going to say, this will be the opposite. And now restarting, is going to stop like that. And I'm not going to bother with this kind of blinking here because it's not possible to solve without doing a lot of redundancy and changing some biases a little bit. But to stop the blinking, because it is bothering me watching it like that, I'm going to press this button for the manual override. And now it's going to stabilize to some position there. And let's do the steering logic next. So basically, in this situation, it shouldn't steer because it sees something on the right. So let's change this here to show this sensor pointing to the right and connect it to steering right. I'm going to put here -1, and here a good value was -0.9. So at the moment, it's not steering to the right. But if I'm going to move the car a little bit in front, then this point here moved in that reddish region. So that means that it does want to steer to the right. And it's going to want to steer to the right a lot like that. And eventually it's going to crash if we don't teach it also to steer to the left as well. And we solved that by filling the remaining part here with blue. So it was like this. Now let's restart this and turn off the manual override. And the car is shaking a little bit like crazy there. But it is kind of steering, except for this crazy thing that happens because, let's see this again. Because now it's just speeding up and all of a sudden it found out it has to turn. So the speed it had was so much that it made it jump to the other side, and then it got confused. So our solution to that was to cap the speed, to make it go not as fast as it can, but at a reasonable speed that the sensor is enough to solve this problem nicely. And we did that by doing this, adding a new node here for the speed. Let's change this to see what's going on, and I'm going to remove the blue and red so that they are not confusing. We have to cut this gray plane here like that. And the good value for this was 20%, so I'm going to put this to -1, and here -20% like this. And this was now connecting here. Let's just remove this, set this weight to 0, turn this one to on to see how it looks like. So 20% means that from here. And we want to combine the two. So not like that. This is now doing the OR. So it's either below this slanted line or below this section. We want to combine them so that we get the intersection of the two. And we can do that by increasing the bias here by 0.1 like this. Let's stop also that fidgeting here, so we can put minus 0.89 for the turning right, and that's going to give a small gap here for when turning so that it doesn't correct its location all the time like that. Let me show you. Here, if we put the sensor to the right and turn on the other two colors, and we really need to use high resolution here. Let's take off also these other things. It's still not very visible, but a gap like this appears there, even if it's minus 0.89. It's a small gap that prevents it from fidgeting like that. Okay, let's put this back here because my computer is starting to breathe heavily, and turn off this manual override, and now the car should be doing very nice things here. Let's have a quick check to see if it's turning properly and if it's visiting all of these regions as well. Everything looks nice on the right. Yeah, turning properly and not crossing the border. So this is exactly what we had last time, but the extra nodes that we have here are to help with the new logic that we are going to create for the stop marking and for the traffic lights. Yeah, so what should happen now is that the car should stop at the stop marking, not just cross there like it's nothing. And the way we do that is the same way that we stop at the road border. Like, we are going to copy this logic for the stop node here as well. So let's try to do it. This is -1. This is -1. And this is minus 90%. Like that. And now let's investigate if this works. We're going to put here the speed, like so. Let's not worry about turning anymore and just keep these gray and green regions there. I think it's actually clearer if we keep just the gray region, because the green one is always going to be the opposite now. So here, with the gray region emphasized, we look what happens when the car is reaching the stop sign. And let's turn on the manual override here. So when it's reaching the stop sign here, we still have this front sensor telling us that it's okay to go because it doesn't see the stop sensor. But if we change this to be the stop sensor, you're going to see that this point is going to be much closer to this side because the stop marking here is closer than the road border. So let's see that. Right, so this did move like that. But now it doesn't have that region that tells it to slow down. So we have to give that to the end result here. And I'm going to create a new node. I think it makes it clearer like this. And let's just copy whatever happens here on the right for now. 0.1, 0.1, 0.1. And let's disconnect this one. So I'm going to put here 0, or let's just remove it entirely and connect this one instead. So now we do get that thing here, but we don't get it anymore for the front sensor because that part is disconnected, right? Let's still focus on the stop for now and just check if it works. So I'm going to remove this manual override, and it goes and it stops at the stop marking, and it never goes anywhere else from here. So this is something we'll have to fix. Let's put on manual override so that this doesn't blink like crazy. And now, because we are stopped at the stop, we want to move again. So looking at this, we would like to have some gray region here on the right. It's okay to move now after we have stopped at the stop. So let's add another link from here. It's only going to be a vertical region. It doesn't depend on the speed or anything like that. When we are really close to the stop marking, it's okay to go. So we can set here a value of +1 like this, and a value here of maybe, let's try 90%, so that this part from here, 90% from here gets gray. So 90%. Now this node needs to be connected as well, and we are going to do an OR here between this one and this one, because if this is okay or this is okay, it's going to accelerate. And you can see this region appearing here. It's not capped, but actually we don't have to worry about capping for now. I think it makes it more complicated. So let's remove this line. And here, instead of having a bias of 0.1, we just have it 0 so that this value transfers like that. And let's refresh to see what is going on. Remove manual override. So the car is slowing down like this, and at some point it continues like that. So it's great. It crashes there, but the logic from here is going to prevent that. It's going to do the capping and everything. Now, it's up to you if you like what happened with the stop. I think that it actually took a little bit too long. So maybe a value of 85. Let's try 87. I think this is now growing too much. I don't want it to be a full stop and to wait seemingly so long there. So I think this is decent how it looks like. In the real world, a stop should mean a full stop, checking if other cars are there, and if not, you can go. But I like things to be a bit faster here. And speaking of other cars, in the demo I have on the website, cars give way to other cars on the right. That works with another sensor like this. It looks fancy, but they're just a bunch of rays in front and to the right that check for cars. If any of them sees something, a sixth input is used to make the car stop. We won't be adding more cars here because it's quite messy, but we will do the traffic lights logic. And that's exactly the same. Think about it. Waiting for a car to pass or for a light to change, is the same thing really, just the sensor is different. We'll move on to the traffic lights in a moment, but first let's reconnect this side so the car doesn't crash like that. I'm gonna replace this link from here to this node in the same way, nothing changes really, so that I can move this one here on this side and connect nicer to this one. Here we have to do an AND, so both of these need to happen for it to work properly. Let's restart, and we can see now how this looks like combined with the cap there. It's slowing down at the stop and now moving to the right. And now as it's moving down, let's change this back to the up arrow, which doesn't have that special part there for accelerating again, which would just make it crash there. But you can see that it's slowing down and it's doing the turn properly. So both logics are combined now in a proper way. It's good if you stop and play with these values, try to inspect things and get your own understanding of this before moving forward. But the last part here really is going to be quite easy. It's a trick that we're gonna do to make the traffic lights also work with as little effort as possible. For that, we are going to move the traffic light here in the middle and the stop to the right. And the traffic light is just going to connect to this node with -1 here. And just like magic, it's going to work. Let's have the car go back to the starting point and see what the traffic light is showing here. You saw it was slowing down and wanted to stop, but then the traffic light just became green. So basically what we want the traffic light to do is like the stop, but we don't want it to start all of a sudden while the traffic light is still red. It's going to stop there and wait there until the traffic light turns to green by itself. So that's the logic. It's actually a simpler logic for the traffic lights than it is for the stop, even though you think that these are more complex. It's the traffic lights themselves that are complex, not the logic that the car is doing. Car just stops. And this is a little bit cheating because I'm assuming that there are no traffic lights and stops next to each other. So that's why this logic works, but it works in most cases. So I'm happy with this. Now the logic here, this or and this and this and, can actually be simplified. So we don't need these hidden layers. I'll show you. Let's remove this node. And car is, wow, it's doing some crazy things now. And connect these ones here as well. So everything connected to this one node there. Now, this is a value of 10 and this is 10. Let's make this one 30. 30. And this one here, let's make it 60, because we're gonna put these weights here to 0.1 and 0.1. And if only one of these is on, it's enough to turn this one on. So we are essentially doing an AND here combined with an OR somehow, with one single neuron there. It's interesting, but it does help to simplify this. And if you restart now, it doesn't work because I forgot this bias here. So now I just want to transfer whatever is here to here, and this bias has to be 0. Okay, so now it should work exactly as before, but with a simpler structure here. We can also get rid of this node. So if your goal is to have less hidden layers, we can do that like so, and connect this one here, and this one here, the minus and the plus. And it's the same logic as before. Let's just check it. And you may wonder, why is this moving here? Well, it's because there are other things, there are other sensors appearing on some other axis. So now this slicing here, it's not anymore a slicing of a cube, it's a slicing of a hypercube. We have not just one more axis, the forward sensor. We have the forward sensor, we have the right sensor, we have the stop sensor. All of them are there somewhere. And here we are just visualizing a slice of that complex hypercube. And you may see some of these movements happening there from time to time. But yeah, you can actually get rid also of this node and simplify this even more. So you could connect all of these directly to that and all of these directly to that and figure out how to do here the knot by a combination of links like that. I'm not going to show you that. That's going to be your homework, but it is possible to simplify this even more so that you need only one hidden layer here. But in my opinion, the logic that I'm reading now is actually clearer for me, for a human to understand. So I can definitely understand here this kind of compound operation that is happening. Like this will turn on when it's greater than 0.6. These two will make it 0.6 exactly. It needs something else. And these are not enough to get anywhere close than that. So this logic here is clear. It needs to have both of these and one of these. So it's actually even simpler than having the more nodes there. And here we just transfer the value here and not to that. If I'm going to have all of the connections copied to the other one, that's just going to make more math in your head. But here the not is very easy for me to understand. I don't know about you. Please keep in mind that we are not really solving self-driving here. This simulation is very simple, and these markings in real, we don't recognize them so easily. I mean, we could, like road markings could send signals and smart cars could pick those up, but that would be very costly to maintain, so car companies have a different approach. They make cars see the world as we do, with a bunch of cameras. They have good reasons for doing that. The roads were made for us, so seeing the same way we do should be enough to solve self-driving. But that gives another layer of complexity here. Large neural networks are used to look at the scene like that and figure out that there is a stop sign there. Not too different from the drawing recognizer we built in the machine learning course, where to get the best accuracy we used a monster of a network. And there we didn't get to 100%. No big deal for the drawings, but here we kind of have to, right? Luckily, stop signs look the same everywhere, so never mind. Anyway, the problem is far more complex, and we're simplifying a lot, is all I'm trying to say. Thanks for watching, and see you guys.